See, in the previous sessions, we have discussed about simplex method. We have discussed the maximization and minimization of using the simplex method. Okay, here one thing that we have to be careful is we are using the less than or equal to inequality. Okay, here also we have less than or equal to inequality. Here also we have the less than or equal to inequality. Okay, this one you don't have to take into consideration. We have to look the inequality sign of the main constraints. Okay, the main constraints here we have three main constraints. All the constraints are having less than or equal to inequality. This is the case of minimization. Okay, we'll see what we did for maximization. So this was a maximization question. Here also we have three main constraints. All the three constraints have less than or equal to as the inequality symbol. Okay. In such cases, what did we do? We actually introduced only one variable that is called as slack variable. Okay. And for all the less than or equal to equalities, for converting them into equal to sign, what did we do? We just added the slack variable. Okay, slack variable is represented by S1 over here. We just added those slack variables. Okay, here also we changed it into equality symbol. Okay, and then we added the slack variable 2. Okay, similarly, third constraint, we made it into equality symbol and we added the slack variable 3. Okay, so this happens when we have inequalities of the type less than or equal to. Okay, so in today's class, we will be seeing what happens if we have the inequality of greater than or equal to or equal to symbol. Okay, so we'll see that in today's class. See, we have here solve the LPP. Okay, here we have two main constraints. We have less than or equal to symbol in the first constraint, but in the second constraint, we have greater than or equal to. Okay, this is greater than or equal to. That is the symbol we have there. Similarly, for the second question, we have three main constraints. Okay, for the first constraint, we have less than or equal to as the inequality symbol. For the second constraint, it is equal to. For the third constraint, it is greater than or equal to. Okay, so in all cases where we have equal to as the symbol or greater than or equal to as the symbol. Okay, any one of the constraints, if they have equal to or greater than or equal to, then we cannot use the usual simplex method. Is it clear? We should not use the usual simplex method that we followed in the last two classes. If we have equal to or if we have greater than or equal to, in such cases, we will have to use big M method. Okay, it is also called as the penalty method. So before we go further, I'll just brief what is the big M method. Okay. So before we jump into the problem, we'll see some of the instructions that we have to follow when we are using the big M method. Okay, big M method, it is also called as the penalty method. This is almost similar to your first simplex method, but there are few changes that you have to make here and there. Okay, so first of all, this is used when the inequality contains greater than or equal to, or we have equal to symbol. Okay, any one of the constraints, if they have greater than or equal to or equal to, then we have to go for the big M method or penalty method. Okay, there is one more method, that is two-phase method. Okay, other than that, we have this big M method. So we'll be seeing big M method in this class. Okay, second instruction, artificial variables are introduced and they are included in the basic variable. Okay, do you remember the basic variable? Okay, I'll just show the basic variable. Okay, so the second constraint over here says artificial variables are introduced and they are included in the basic variable. See, in the previous problem, I'll show this table. This is what we did for the previous one. See, we have to include, this is the basic variable. In this basic variable, we have to include artificial variables. Okay, here we have included only slack variables. Okay, slack variables because we had only the inequality symbol of less than or equal to in the previous problem. So in this previous problem, we have included only slack variables S1, S2 and S3. Okay, but if we have the constraints of the type greater than or equal to, or if we have the constraint of the type equal to, then we have to introduce artificial variables also into this basic variable. Okay. Now this is represented by B. What is this? This is the coefficient of basic variable. So whatever is the coefficients over here, the variables, sorry, whatever be the variables over here, we will mark the coefficients of these variables over here. Okay. For example, we have S1, S2, S3 here. Okay. Corresponding coefficients of S1 is 0, S2 is 0, S3 is 0. So that is why we have 0, 0, 0 over here, which is the coefficients. Okay. So that is represented by CB. Now what is XB? XB is also called as a solution. This is actually the value of basic variable. Okay. This is basic variable. It is represented as S1, S2, S3. The coefficient of the basic variable is represented by CB, which is in this case 0, 0, 0. And what is XB? XB is the value of this basic variable. Okay. And it is represented by XB. Okay, it is also called as the solution. Okay, so we'll go further. The third instruction there is the artificial variables are driven out in the first iterations that you will see when we do the problem. Fourth instruction, we assign a very large value minus m to each of the artificial variables as coefficients in the maximization objective function. Okay, in the previous case, in the objective function we added, I'll show you. See, in the previous case, see we had, this is our objective function. In the objective function, we have added the slack variables, okay, which we entered in the constraints. We have three constraints. We have three surplus variables here, slack variables here, S1, S2, and S3. All those slack variables, we have introduced them even in the objective function, okay, with coefficient as 0. Okay, so that in effect, there is no change for the objective function, but we have to introduce them in the objective function also. Okay, so three slack variables, we have introduced them in the objective function also. Similarly, in the case of big M method also, we are introducing artificial variables. Okay, artificial variables have to be added in the objective function also. And what does this instruction say? In the objective function, the artificial variables should have a coefficient of minus m. Okay, you will understand it when we do the problem. And finally, m is called as the penalty. Okay. So before we go into the problem, there are a few things that you must understand in regarding the negative value and highest negative value. So we have over here one question. Identify highest negative value. Okay, first one is 7 minus 4m, 6 minus 6m plus 6, 2 by 3 minus 9m. Okay, in this, how do we select the highest negative value? Okay, you have to remember that we have told over here. See, we assign a very large value minus m. So this m, that value is actually a very large number. Okay, you have to consider m as a very, very large number. So for identifying the highest negative value, you don't have to consider these numbers. Sorry, these numbers. Okay, over here you don't have to consider 7. Okay, here you don't have to consider the 6. Here you don't have to consider 2 by 3m. Sorry, 2 by 3, because we have to consider only the coefficient that comes along with m. Okay, because m is the highest. It is a very large value. Okay, so you have to consider only the coefficient that comes along with m for deciding which is the highest value. Okay, so here in this case, you need to consider only minus 4. Here you need to consider only minus 6. And here you need to consider only minus 9. Okay, so when you're comparing minus 4, minus 6, and minus 9, which is the highest value? Which will be the highest negative value? Which will be the highest negative value? We are comparing minus 4, minus 6, and minus 9. Very good. The highest negative value compared to all these three values is minus 9. So that is corresponding to the last number here. So we understand that 2 by 3 minus 9m is going to be the highest negative value. Okay, so in this case, you don't have to consider 7, here 6, and here 2 by 3, because m value is not associated with these values. Okay, you need to consider only the coefficients of the values for which we are having m. Okay, so here we have minus 4, which is associated with m. Here we have minus 6 that is associated with M. And in this last number, we have minus 9 which is associated with M. And we are considering the three numbers there. Minus 4, minus 6 and minus 9. Minus 9 is the highest value, negative value. So we say that the last number here, 2 by 3 minus 9 is the highest negative number when we consider the three numbers. Okay. Again, we have another question. Identify the highest negative number in these two numbers. Can you identify them? Highest number in these two. We have already told that we don't have to consider 5 or 4 because M value is not associated. So we will consider the coefficient of M value. Okay. In this case, it is minus 3 which is associated with M. In this case also, it is minus 3 which is associated with M. Okay. In such cases, we will have to consider the other number. Okay, so this is an exception. In such cases, you will have to consider the other number also. Here we have 5 minus 3m. Here we have 4 minus 3m. Okay. Now what you need to know is 5 minus 3m or 4 minus 3m. Which will be the highest negative number? 5 minus 3m or 4 minus 3m. Okay, if you have a doubt, what you do is just substitute some value. Okay, here I am taking 5 minus. Okay, instead of 3m, I'm taking a bigger value like I'm taking 10. Okay, here also, here I have 4 minus. Instead of this minus 3m, I'm taking the value 10. Okay, here also it is 3m, here also it is 3m. So I can take the same value, take some very big value. Okay, for example, in this case, I can take 10. Okay, so it is 5 minus, instead of 3m, I'm taking 10. Here, 4 minus, instead of this 3m, I'm taking 10. Okay, so when I do this, tell me the value. Here I will have minus 5 and here I will have minus 6. Okay, so which is the highest negative compared to these two numbers? Minus 5 or minus 6? Very good. Minus 6 is the bigger value. Okay, higher negative number. So in my case, 4 minus 3m will be the, yes, 4 minus 3m will be the highest negative number. Okay, is it clear? Okay, so in such situations where M value has the same coefficients in both the numbers, in such cases, you will have to consider the other number also. Okay, if you have any doubt, just substitute some value and then find it out. Okay, a value which is subtracted from a bigger number, okay, or a value which is subtracted from a smaller number. Okay, the smaller number will have highest negative value. Okay, the number which is subtracted from the smaller value will have a highest negative number. Okay, I hope it is clear for you. Okay, and one more thing is there. If all Cj minus Zj, we have already seen, right? In all simplex table, we calculate Cj minus Zj. Okay, in maximization case, our Cj minus Zj should be less than or equal to, all Cj minus Zj should be less than or equal to 0. Okay, only then we can say that we have reached the optimal condition. Okay, in begin method, there is a small change. If all Cj minus Zj is less than or 0 and the basis, that is the variable. We have already seen what is basis, right? Okay, the second column in the feasible table, in the simplex table is called as basic variable. Okay, so if all Cj minus Zj is less than or equal to 0 and the basis, that is the basic variable, has artificial variables. Okay, we have reached the final condition wherein we got all Cj minus Zj as less than or equal to 0. And at that time, if the second column contains any artificial variables, then the LPP does not have any feasible solution. Okay, in that case, the LPP will not have any feasible solution, infeasible solution. Okay, I hope you remember the graph of the infeasible solution. Okay, we have already completed the infeasible solutions graph. So, now, the simplex table will approach the infeasible graph. Okay, it will be the same for the infeasible graph. Okay, so you don't have to worry about this. We'll solve a problem and then you will understand more. Okay, so we have a problem here. Okay, see, solve LPP using the question will be either to solve LPP alone. Okay, in that case, you have to check the constraints and decide which method we have to use. Okay, if all the constraints are less than or equal to type, then we can go for the simplex method. Okay, but in our case, we have one constraint having less than or equal to But unfortunately, the second constraint is greater than or equal to. Okay, in that case, we have to understand, we will have to use the big M method. Okay, big M method is also called as the penalty method. Okay, so this is our objective function and we have two constraints here. So initially what we do is we have to introduce already less than or equal to type. We have already seen, we have introduced slack variable for less than or equal to symbol. Okay, but in the case of greater than or equal to, we have to use, instead of slack variables, we have to use surplus variables and artificial variables. I'll just write it down. Okay. By introducing slack variables, surplus variables, and artificial variables, the LPP is as follows. Okay. In this case, what happens? First of all, we'll write the constraints subject to. The first constraint is 2x1 plus x2 less than or equal to 2. Okay, so here we have 2x1 plus x2. Instead of this less than or equal to symbol, we will introduce the slack variable s1. Okay, and then we'll put equal to 2. Okay, so first constraint is over. Now we have to consider the second constraint. Okay, so 3x1 plus 4x2. Here we have a greater than or equal to symbol. So instead of that, we have to subtract. This is called as surplus variable. Okay, I'm representing it as S2. Okay, S2 is the surplus variable plus I'm adding the artificial variable. I'm writing it as A1. Okay, this is equal to 12. Okay, so just remember, if you have the less than or equal to symbol, you just have to add the surplus variable, slack variable S1. Okay, so for less than or equal to symbol, you have the variable called as slack variable. Okay, if it is greater than or equal to, you have to, okay, subtract surplus variable and add artificial variable. Okay, artificial variable. In the case of less than or equal to, you are adding the slack variable. Okay, is it clear? So this is what happens. Now, if the inequality is equal to, okay, in that case, you will be adding the artificial variable. Okay, you don't have to use the surplus or slack variable. If it is equal to symbol, you just have to add the artificial variable. Okay, just keep this in mind so that you'll be able to solve problems easily. Now what we do is we have the non-negativity constraints. Okay, for example, x1. Here we have x2, comma, we have added the slack variable s1. We have subtracted the slack surplus variable s2. Okay, comma, a1. All of them should be greater than or equal to symbol because this is our non-negativity constraint. Okay, is it clear? Now, with this, our LPP is not over. We have to add all these variables. Okay, bring all these variables into the objective function. So, max z is equal to 3x1. Here we have max z is equal to 3x1 plus 2x2. Okay, 3x1 plus 2x2 plus, see over here, in the first constraint, we introduced the slack variable s1. This one adding s1. What will be the coefficient of s1? It will be 0. Okay, then in the second constraint, I have subtracted s2, which is called as a surplus variable, and I have added the artificial variable. Okay, so I have to add over here s2. What is going to be the coefficient? Again, 0 is going to be the coefficient. Then minus, I have an artificial variable here. Okay, in the instructions, I have already written, if we are using any artificial variable in the constraint, then we have to introduce the artificial variable into the objective function with the coefficient minus m. Okay, minus m a1. Okay, so this is how the objective function will change. Okay, just listen here once more. S1, we have added S1 here. When we are introducing S1 into the objective function, you have to add S1 with the coefficient 0. Okay, similarly, here you have subtracted S2, but even though you have subtracted S2, in the objective function, you have to add it. Okay, even here you have negative S2, but in the objective function, it will be positive S2 with the coefficient of 0. Okay, over here you have added A1, but in the objective function, you will have minus M as the coefficient of the artificial variable in the objective function. Okay, hope it is clear. Okay, so this is how the objective function will change. Now, after writing so much, what do you do? We will go for the simplex table. Okay, so this is the initial simplex table. Okay, what do we have here? Here we have Cj, which is the coefficient of the objective function. This is our objective function. Changed new objective function. So I'm writing 3. Here I have 2, then I have 0, then 0, and I have minus n. Okay, what are the variables corresponding to all these coefficients? I have in the first one, I have x1. Second one, sorry, can you see that? Okay, the coefficients were 3, 2, 0, 0, and minus m. That I have written over here, 3, 2, 0, 0, and minus m. Next, we have to write the variables corresponding to these coefficients. Okay, 3, we have x1. So, just below 3, I have written an x1. 2, I have x2. Okay, 2 is x2. 0 is corresponding to s1. This 0 is corresponding to s2. And this minus m, it corresponds to artificial variable 1. Okay. Next one is we have over here I have the coefficient of basic variable b, which is represented as CB. Okay, next one is the basic variable. Basic variable, it is also called as basis. Okay, basic variable is represented by the letter B. Okay, over here I have the value of basic variable. It is also called as solution, and it is represented by the letter XB. Okay, in the last column we have minimum ratio. Hope you remember all these terms. Okay, so what do we do first? We will take the constraints from here, and we'll put the coefficients in the simplex table. Okay, here we have 2 corresponding to x1. So in the first row, I'll write 2 corresponding to x1. Here we have x2 with coefficient 1. So I'll put 1 there. S1, it is having coefficient 1. So I write 1 there. Do we have S2 in the first constraint? No. So I'll put 0 for S2. And we don't have artificial variable also in the first constraint. So I'll put 0. Okay. Take the second constraint. I have 3 corresponding to x1. So I put 3 there. Can you see that? Okay, 3. Okay. Next one is 4 corresponding to x2. So I write 4 there. Next one, do we have S1 here? No. So I'll put below S1, I'll put 0. I have S2 with coefficient of minus 1. So I'll put minus 1 here. And then I have artificial variable A1. Okay, what is the coefficient? It is 1. So I'll write 1 there. Okay. Now, the first constraint, after equal to, I have 2. So in the solution side, I will put 2 there. For the second constraint, after the equal to, I have 12. So in the first constraint, I will write 12 there. Okay. Now, how do we decide the basic variable? We have to consider the identity matrix. Okay, identity matrix over here. Can you tell the identity matrix? Okay, in case of 2 cross 2 matrix, the identity matrix will look like 1, 0, and 0, 1. Okay, so you have to check out for such a column from this simplex table. Okay, 1, 0. Where do I have 1, 0? I have over here. Okay, 0, 1. Where do I have 0, 1? It is over here. Okay. So the variables corresponding to these 2 columns will form the basic variable. Okay, here I have S1, the coefficient is 0. So the first row I will write S1 and the coefficient is 0. Okay, in the second row, my identity matrix comes over here. Okay, I have A1 and the coefficient is minus m. Okay, so I will write over here A1 and it is minus m. Okay, S2 does not come into the basic variable. Okay. Next, what do? We go for Zj. Okay. Then after that, we go for Cj minus Zj. Okay. Zj, we will actually multiply this column with each of the columns in the simplex table. So 0 into 2 plus minus m into 3, it is minus 3m. Okay, similarly 0 into 1 plus minus m into 4, it is minus 4m. Similarly, minus m into 0 is 0. You don't have to consider the first row completely because you're multiplying it with 0. So you can just eliminate it. Okay, minus m into these values will only come over here. Okay, next one is minus m into minus 1, that is m. Minus m into 1, it is minus m. Okay, now this also you can calculate here minus m into 12, that is minus 12m. Okay, now what is Cj minus Zj? Cj is this value here and Zj is, we have already got it now. So 3 minus 3m. Okay, 3 minus of minus 3m. Correct now? Cj value is 3, then 1 minus. What is Zj value here? It is minus 3m. So how do we get it? 3 minus of minus 3m. Correct? Okay, 3 minus of minus will become plus. So it is 3 plus 3m. Okay, you cannot solve it. You will have to write it like that itself. Okay, so it is 3 plus 3m. Okay, similarly here 2 minus minus 4m. So it will become 2 minus of minus is plus 2 plus 4m. You cannot solve this. You will have to just write it like that. Okay, 0 minus 0 is 0. 0 minus m, it is minus m. Minus m, minus of minus m. Okay, how is it? Minus m, this minus m, then minus of, what is the value here? Minus m. So it is minus m, minus of minus m will become minus m plus m. So we'll have 0. Okay, so this is our Cj minus Zj value. After doing this much, what will we do? We'll check out for the highest positive value of Cj minus Zj. Okay, over here all the values are, here this value is a positive value, here this value is a positive value, then we have 0, minus m and 0. Okay, for optimality condition, we should have all the values as negative or 0. Okay, but in our case, these two numbers are positive numbers, right? This is not a negative number. Here we have symbol plus, here also we have symbol plus. Okay, so 3 plus 3m is also positive, 2 plus 4m is also positive. Okay, now we have to decide which one is more positive. Correct? Because Aj minus Zj, we have to select the column here based on the most positive value of Cj minus Zj. Correct? Okay. So in our case, can you tell me which is most positive number? Is it 3 plus 3m or 2 plus 4m? Very good. It is 2 plus 4m because we need to consider only the coefficient of m value here. Okay. Here we have 3. Here we have 4. Okay. 3 is lesser than 4. So 2 plus 4m is the bigger value. Okay. So we will take this as the incoming vector. Okay. This will be our incoming vector. Now we have to decide for the outgoing vector. How do we decide outgoing vector? We have to calculate minimum ratio. Minimum ratio, how do we do? It is xb divided by the key column. Key column is x2 here. Okay. So it is 2 divided by 1. 2 divided by 1, which is 2. And 12 divided by 4. Okay, which is 3. Which is the smallest value? It is 2. So we have the first column as the outgoing vector. Okay, so in the next simplex table, instead of S1, we will have the value of X2 because X2 is the incoming vector, S1 is the outgoing vector. Okay, this will go out and X2 will come inside. Okay, then we have few row operations to be completed. Okay, see over here, this is our key column. So we have to start the row operations starting with the key row. Okay, key row, from there only we'll start the row operations. So what will happen? We have the incoming vector, which is our incoming vector. We'll just write it down. We have the incoming vector. Incoming vector is x2. Okay, x2, and we have the outgoing vector. Outgoing vector is the vector that is going outside, that is S1. And then we have the row operations. What will be the row operations? R1 new is equal to R1 old. See here row 1 is same as the key row. Okay, so instead of R1 new, I can also write as key new. Okay, instead of R1 old, I can write it as key old. It is the same thing. Okay, So what do we do with the key row? We'll actually divide the key row with the key element. Okay, over here in our case, what is the key element? 1 is the key element. Okay, so R old divided by 1. Okay, will anything change? No, when you're dividing the number with 1, nothing will change. So it will be same as R1 old. Okay, this is also called as key old. Okay, so R1 new, we are not changing anything because we are just dividing by 1. There is no change in effect. So we'll go to R2. Okay, R2 new is equal to, how will it change? R2 old minus of the number above or below the key element, which is the number 4. Okay, 1 is our key element, the number above or below the key element corresponding to the second row. Okay, so corresponding to second row, we have 4. Okay, minus 4 into, we'll write the value of R1 new, which is also called as key new. Okay, R1 new. Okay, so just tell me the numbers. What are they? It is 3, 4, 0, minus 1, 1, and 12. I'm writing it down. Okay, 3, 4, 0, minus and 12. Okay, minus. I'm writing this minus over here. Minus of 4. See, this 4. Okay, I'm writing it everywhere. Into, it is R1 new. R1 new is same as R1 old. It is the same row here. So it is 2, 1, 1, 0, 0, and 2. 2, 1, 1, 0, 0, and 2. Okay. So tell me the values. This is 3 minus 8, which is minus 5. This is 4 minus 4, it is 0. Minus 4 into 1, it is minus 4. Here we have minus 1 into 0, that is minus 1. Here we have 1 minus 0, it is 1. Here we have 12 minus 8, which is 4. Okay, so take down those values and form your new simplex table. Okay, on first row we have Cj. Cj is the same, there will be no change. You can just copy down the values of Cj from the previous table. It is 3, 2, 0, 0, and minus m. Okay, 3, 2, 0, 0, and it is minus m. It is x1, x2, s1, s2, and a1. Here we have b. Here we have the coefficient of basic variable cb. Here we have the value of the basic variable, which is represented by xb, and over here we have the minimum ratio. Okay, take down the rows. Okay, first row is going to remain the same because we divided it by 1, so it is the same thing. 2, 1, 1, 0, 0, and 2. Okay, 2, 1, 1, 0, 0, and 2. Okay, next one. We have 3, 4, 0, 0, minus 1. So we have to put the new values for the second row. New values, we have got it. We have found it out from here. Minus 5, 0. Minus 4, minus 1, 1, and 4. Okay. Okay. So after that, we have to put the vectors which are going. Okay, S1 will go outside, and instead of that we have X2. The coefficient of X2 is 2. Okay, so X2, coefficient of X2 is 2. The next basic vector, it will remain the same, A1 at minus m. So I will put A1 at minus m. Okay, after getting so much, we will calculate Zj and Cj minus Zj for optimality condition. Okay, Zj, just multiply. It is 4. 2 into 2 is 4. Okay, plus minus m into minus 5. So it is 4 minus into minus will become plus. Here m into 5, it is 5. Okay, similarly 2 into 1 plus minus m into 0, that is 2. Next one, 2 into 1 plus minus m into minus 4, that is 2 plus 4m. Next one, 2 into 0 plus minus m into minus 1, that is m. And 2 into 0 plus minus m into 1, that is minus n. Okay. Similarly, you can calculate for xb also. 2 into 2 plus, that is 4. Okay. Minus m into 4, that is minus 4. Okay. We'll calculate Cj minus Zj. Cj is 3 minus 4 minus 5m. So how will you write it? See 3, this 3. Okay, 3 minus of Zj value is this one. Okay, 3 minus of Zj value 4 plus 5m. Okay, which is 3 minus. This minus will go here. Again, this minus will go here. 5m. Okay, 3 minus 4 is minus 1. This value you cannot subtract with 3 or 4. Okay, so leave it like that itself. Minus 1 minus 5m. Okay, so this value will go over here. Minus 1 minus of 5m. Okay, is it clear? Next value 2 minus 2, it will become 0. 0 minus, how will it become? This value 0 minus 2 plus 4m. Don't forget to put this bracket here. Okay, this negative number here, negative number, we have to take it for both 2 as well as 4m. Okay, so it will become minus 2 minus 4m. Okay, minus 2 minus 4m. 0 minus m, it is minus m. Minus m, minus of minus m. Okay, how will this number become? Minus m, which is this minus m, minus of this minus m. Okay, so minus m minus will become plus, minus m plus m, which is equal to 0. Okay, so over here I will put 0. Okay, now tell me, have you reached the optimality condition? Check all the Cj minus Zj and tell me. In maximization case, all Cj minus Zj should be less than or equal to 0. It should be either a negative number or it should be 0. So have you reached the optimality condition here? Okay, have you reached the optimality condition here? Yes, we have reached, because over here m value has a coefficient of minus 5. So in this case, it is a negative number. Okay, over here it is 0. Over here we have minus 4m. So m is having a coefficient of minus 4. So it is a negative number. Here, over here also it is m is having a negative 1 as the coefficient. So it is a negative number, and over here we have 0. So all Cj and Zj values, it is either less than or equal to 0. Okay, so what happens? This, we have reached the optimality condition. Okay, now what did we see in the note condition? This is the instruction we saw. Okay, if all Cj minus Zj is less than or equal to 0, so we have reached that condition. Okay, and the basis, that is the basic variable, has artificial variables. Okay, then the LPP does not have any feasible solution. Okay, so here what happens? We have reached the optimality condition because all Cj minus Zj is less than 0. But see over here, this is called as our basic variable. Okay, this is our basic variable represented by B. Over here we have artificial variable also in the basic variable. Okay, so in the note, it says that if we have artificial variables, okay, in that case, we will not have a feasible solution. Okay, artificial variable should not be there. Okay, only in such cases we will have a feasible solution. But in our case, artificial variable A1 still remains in the basic variable. So we don't have a solution to this problem. It is an infeasible solution. Okay, so what will we write? I will write it here. Okay, since all Cj minus Zj is less than or equal to 0, but there is artificial variables in the basis. Basis is represented by B. Therefore, it does not have an optimal solution. Optimal solution or feasible solution. The same thing. Okay, is it clear till now? Okay, so this is how what happens. We took the example of the maximization problem and then we did it. We got that all Cj minus Zj, we got it less than or equal to 0. But unfortunately, in the basis, there was a artificial variable. So we say that even though we have optimal solution, we do not have any feasible solution.